Okay, this is the lecture 1 of computational microelectronics. Although I have finished my first lecture, offline lecture, from 9 o'clock in this morning, but it is not recorded. So I wanted to make another, once again repeating my lectures in a short form in this in this lecture. Okay, so lecture 1 is just describing what is technology computer aided design. Although I have spent 75 minutes in the offline lecture, I will make it quite short. So TCAD is a word for technology computer aided design. So since my students in this course is all come from um, circuit design lab, so first of all I wanted to start from this slide. So there are various ways to represent a two input NAND gate. For example, this is a logical symbol and this one is circuit schematic. So usually you learn this kind of logical symbol when you are second year in your college. So after that, typically in the course microelectronics, you learn about MOSFETs, transistors. After that, combining them into in this way, you understand this circuit is working as a logical two-input NAND. However, this is just a circuit schematic and not in the physical reality. When you go to the more higher course, then you learn that in order to design certain circuit, you have to have a layout. And this is the layout of your two input NAND. So, as a circuit designer, you can have logical symbol, circuit schematic, or even layout. However, none of them is, in my opinion, physical reality. Then what is the physical reality? In my opinion, this is the physical reality. This figure shows the three-dimensional structure of a two-input NAND gate. So in this picture taken from synopsis, you can find that this green region silicon and this one is corresponding to insulator and yellow and purple as metal lines. So although you have a certain abstract view on your logical function, in order to make it true, then we have to build this quite complicated structure within really small physical dimension. So that is the technology that makes it true is called as a semiconductor technology. So semiconductor devices technology always have quite a challenging goal. So this figure is taken from TSMC's last IDM presentation. So compared with their own N5 node, their enhanced N3 node has better performance in terms of area and speed. This direction is corresponding to the smaller area, good direction. Also, this direction is higher speed, also good direction. Although they provide three different options, but all of them have the same trends: smaller area and higher speed with reduced power efficiency. So, or improved power efficiency, so reduced power consumption. So yes, this is a quite big deal to make it true. So And more important thing is TSMC is not the only company to do that. There are two more companies trying to achieve this goal. So trial and error will make serious loss in the company's faith. So we have to minimize the trial and error, and we need a guide to secure the success of technology development. So TCAD is used to guide technology development. It can have a process simulation, also device simulation. So they will be explained later. But before talk about process simulation and device simulation, just to consider the term called CAD, computer aided design. This figure shows typical CAD drawing. CAD drawing means that if we have a certain mechanical structure or buildings, airplane, car, if we have complicated structures, it would be very difficult for us to design with our hand drawing. So CAD was originally used for computer aided design. The structure or shape was of interest. However, when you say TCAD, technology CAD, it is not just for shape of our transistors. So when we have technology CAD, TCAD, it is more or less related the structure and electrical performance of our devices, semiconductor devices. I understand this word technology is too broad to be used for only for semiconductor device technology, but this is not my invention, but our early pioneers in this field just named it as TCAD. And TCAD is also quite much related with EDA, electronic design automation. As a circuit designers, many people are related with this field. They just lay out, and so this layout is from this layout the parameters are extracted and design is verified, and this verification result is just a feedback into the designer, and they reiterate this layout. However, all of these EDA works are based on spice model and behavioral model of our technology. So TCAD can provide some information. For example, PDK or behavioral model is the data provided from this TCAD field. So TCAD is not like an academic interest only. So this is a really serious industrial application. So we have so many TCAD vendors. TCAD vendors are companies offering TCAD tools. There are many TCAD vendors, and representative ones are shown here. For example, Synopsys, Silvaco, GTS. So, and there are many other smaller companies. So if you are really serious about TCAD, then you have to get the license from those companies. However, in this course, we try to build our own course. Sometimes people say, don't try to reinvent the wheel. However, in this course, I wanted to ask you to build or reinvent the wheel. For what? For this semester, I wanted to ask you to do for your deeper understanding on the device and process. I think that this is the best way to understand the device and process. So when you develop your own code, that will give you tremendous experience on this subject. So I strongly recommend to do that. So this is a simulation flow, and this is a technology development flow. Yes, here we have one node, quite much simplified device fabrication. Of course, we all understand this device fabrication is actually at the heart of device technology. But anyway, in this simplified view, let's assume that after about 2 months long fabrication, we have experimental data. And let's assume that this experimental data does not meet the criterion for our technological goal. Then what should we do? Of course, since the target goal is not matched, we have to change our certain procedure to make our transistors. Then which one should be changed, or how much should a parameter be changed? That is quite an important question. If you make any mistakes in that decision, then it will delay your development time at least 2 months or 3 months. So that is a huge loss in your company. So of course, eventually you have to verify your decision with your experimental data. However, just blindly split every parameters and wait for a long time, that is not the viable option. So we have to be more clever. So TCAD can help you in that aspect. So from data analysis and comparison with TCAD data, then we can find a newer process simulation, process options, and process simulator can give you the structures expected from a new process steps. Then within this device structure, we can perform device simulation and can get also certain estimated or predicted value of our device. Then when we have a certain feeling that this procedure this new option can improve the performance, then now we can make it once again and get the experimental data. Of course, at once we cannot solve all the problem. However, by iterating this way, eventually we will get better and better result. So eventually we will achieve the goal. Of course, even without this TCAD enrollment, if we spend quite a long time and huge resources, then eventually we can get or can meet the requirement. However, that just means that failure of your technology development in time. So it is just related with the failure of your research organization. So TCAD is really heavily used for every company, every serious company on the technology development. And you can understand they means that these TCAD tools have two pillars. One is process simulation and one is device simulation. Process simulation is related with the feasibility of device fabrication. The wanted structure, desired doping profile, or desired stress profile can be obtained by this designed process or not. That is estimated by this process simulation. After that, under the given device structure, whether that structure can give us the desirable current level or not, or sufficient leakage level or not. That is estimated by this device simulation. So I have prepared quite a few slides for device simulation and process simulation. So this figure just shows planar MOSFET. You know, planar MOSFET is already an old technology. However, even in this planar MOSFET, the structure is not that simple. Usually, in a textbook, we just visualize this two-dimensional cross-section of our structure. However, in reality, even in this planar MOSFET, we have the end of our structure and there is boundaries. And usually the device has many different materials: silicon, silicon germanium, oxide, nitride, hafnium oxide, whatever. And also we have quite rapidly varying doping profiles like N-type doping profile and P-type doping profile. All of these features makes the analytic estimation or humans insight on this device structure almost impossible. We have to rely on the computer simulation whether that desired structure can be actually manufactured or not. So that is one of our process simulation. So this slide just lists 8 different process steps typically used in the semiconductor manufacturing. So gray one is not directly covered in the process simulation. For example, at the beginning of chip fabrication, first of all, we have to buy the wafer. However, we believe that we can buy quality wafers from specialized company. So usually in the process simulation is not interested with the wafer itself. After that, we can do the oxidation. Yes, oxidation is quite important because that really determines the channel of our transistor. And photolithography. Okay, photolithography is of course in the scope of process simulation. However, since photolithography is so much important, usually photolithography is usually done by so-called optical proximity correction, so OPC tools. So usually in the case of process simulation, photolithography is just defining certain geometrical structure of a photoresistor. So photolithography is not directly covered in this semester. After that, certain exposed part can be etched, and etching is a really important topic in the process simulation. After that, ion implantation or thin film deposition can be done. This figure just shows the ion implanted profile, and here you can see that there is a photomask, and only for this open window implanted ions can be found. And here this one shows that the profile after 20-second diffusion, 40-second diffusion, and 60-second diffusion. And of course, since we have done the diffusion process, the impurities are moved deep into the substrate. Yes, qualitatively, everybody understands this feature. However, what is the expected doping density at the depth of 300 nanometer after 60-second diffusion? So human being cannot answer that question. So we have to rely on the computer simulation once again. Other process steps are all important. For example, interconnect. This is really quite important. And EDS and packaging. Especially nowadays, packaging is regarded as one of the most important process steps in semiconductor industries, because they wanted to do some integration using packaging. However, typically speaking, when we talk about process simulation, usually we are more or less interested with this front end of line processes. So also photolithography is done by OPC. So usually we are more or less interested with oxidation, etching, deposition, and ion implantation. And now let's go to the last slide. I have prepared one single slide for device simulation. As you can see, the process simulation have many different subroutines. For example, if you build a code for ion implantation, good. However, your code cannot be applied to the diffusion simulation or etching simulation. Those processes have completely different natures. So you have to each code for each process. However, in the case of device simulation, the rule is quite simple. We just wanted to describe the electronic motion. Motion of electrons are described or simulated by our device simulation, because electric current is just a direct result of electronic motion. So it is enough for us to consider just electronic motion. And they all share the same rule. I mean that since electrons are quantum mechanical objects, so quantum transport would be the best tool for transport estimation. However, there are so many non-ideal effects which are difficult to be captured in the quantum transport simulation within the restricted resources. Then usually we adopt some semi-classical description. However, this semi-classical description governed by Boltzmann transport equation is sometimes too complicated. Still, we make another simplification and we finally arrive this drift diffusion model. And this drift diffusion model is the workhorse of today's TCAD model. So typically say when we say TCAD device simulation, we simply pointing out this drift diffusion model. By further simplification, we can build a compact model. However, this compact model is not regarded as TCAD, and there we have the boundary between TCAD and EDA. Yes, we have a boundary here. And this drift diffusion model is actually a set of partial differential equations. So its analytic solution is not available. So we have to do some numerical simulation. So to get the numerical solution. So this is the end of our first lecture, lecture 1. Let me just summarize today's lecture. So, although circuit designers represent certain logical function with different rules, but eventually they should be realized as silicon. So the semiconductor device technology makes it possible. So when we have a quite tough development goal for semiconductor device technology development, we need a certain help from computer simulation. That computer simulation is called as TCAD, Computer Technology Computer Aided Design. And they have two pillars. One is process simulation and one is device simulation. In process simulation, we just think about the feasibility of a given structure. Can we make it or not? That is done by the process simulation. Once a structure is made by the process simulation using certain transport theory, we estimate the electrical performance of that structure. So if the performance is meeting the goal of technology development, everybody will happy. However, in reality, it's not. So then we must iterate process simulation, device simulation, and fabrication. Process simulation, device simulation, fabrication. By repeating this routine, then eventually we can fastly approach to the successful technology, next generation technology. Okay, thank you for listening, and in the lecture 2 we will talk about how can we set up our development environment. Thank you and see you later. Bye.